Um, Thank you. Thank you for the invitation to speak, to present present some of my recent results. So this talk is going to be a talk that is mostly qualitative, not quantitative. Even though all the results are, of course, quantitative, I will not bother you with many technical details. I will rather emphasize the big picture. Also, please feel free to ask questions during the talk. Do not wait until the end. So hydrodynamics is an established field with a venerable history and many applications. However, today I will not talk about applications. Rather, I would like to highlight some foundational questions that only came to light in the last few years. So what is hydrodynamics? It's basically a set of equations that tell you how stuff flows. Stuff can be water, air, can be cold atomic cloud, hot primordial matter in early universe, electron fluid in the solid, etc. And if you remember yourself as a student, so as I think of myself as being a student, when I open a book with hydrodynamics or fluid dynamics in the title, I would see there derivations and approximations and applications, and all of this is going to be mixed together. So if as a student, you're also learning about calculus and partial differential equations at the same time, it can be hard to see the big picture. But the big picture of hydrodynamics is in fact quite simple. So here it is. So fundamentally, hydrodynamics is a classical theory. So I emphasize is a classical theory. I will talk about how to go beyond classical later. It's a classical theory of things that cannot disappear. That is, they are conserved. And the way we teach our students conservation laws, we write them like this. So time derivative of some conserved density is equal to minus the divergence of the flux of that conserved density. So that conserved quantity can be energy, momentum, number of particles, and so on. So you need one more ingredient to do something useful with it. So it's a classical theory, and you have this classical conservation equation. And so in 3 special dimensions, you have 4 unknown functions, 1 scalar here and 3 vectors here. And you don't know what much to do with this, except if you just assume that the flux of your conserved density is a function of that density itself. Then you have one equation for that conserved density that you can in principle solve. And so that's how hydrodynamics proceeds. So assuming something like this is called constitutive relations. So more generally, what you do, you take some useful quantities, not necessarily the density, but some useful quantities that I will call gamma. This could be temperature or the fluid velocity. And you express your densities and the fluxes in terms of those useful quantities. This can be useful for symmetry reasons, for example. And then you have only equations for these gamma, the useful quantities that you can in principle solve. Just to give the simplest example of how this works, let's take our conserved density to be energy, and let me take my useful quantity to be the temperature. Then my conserved density is energy density as a function of temperature. And the constitutive relation, I now have to express my energy flux as a function of temperature. Now, energy flux is a vector and temperature is a scalar. And the simplest way to make a vector out of a scalar is to take the gradient, which I did right here. And there is some coefficient out in front, which is the heat conductivity. And then it's pretty easy to see that when you take these 2 relations and substitute them into the conservation law, when you look at deviations of temperature from equilibrium, you get the diffusion equation, which is like this, right? So one derivative with respect to time comes from the left-hand side here, and 2 derivatives with respect to 2 spatial derivatives, they come from the right-hand side, one from the divergence and one from this gradient right here. So that's how you get diffusion equation in hydrodynamics. So more generally, so that's how hydrodynamics works. In practice, we have these conservation laws, and then we have these constitutive relations that express the densities and the fluxes in terms of these useful quantities. So as we have seen on the previous slide, these relations can in principle involve gradients. And this can be gradients of higher order as well. And the procedure is the same, whether the fundamental constituents are classical or quantum, relativistic or not, normal fluid, superfluid, magnetic fields present or not, chiral fluid or not, it all works exactly the same. So if you choose by hand just to throw away all the terms that have derivatives of your useful quantities, you get what you call perfect fluids, and the conservation equations are called the Euler equations of hydrodynamics. If you by hand throw away all the terms that have 2 and more derivatives, you get what you call viscous fluids, and the equations are called the Navier-Stokes equations. If you throw away 3 or more derivatives and only keep up to 2 derivatives, you get what you call second order fluids. The equations are called Brunet equations, and so on. So this is the summary of what hydrodynamics is. About every theory in physics, we have to ask these questions. Every theory is only approximately correct. It's only approximately correct, right? Not precise. It's limited by its domain of applicability. And we have to ask these questions about every theory. One is, do the equations of our theory make sense? Number 2, can we improve the equations to capture more physics? And number 3, what kind of physics is beyond our equations? So what will follow are three short stories, one related to each of those questions. So the first story is this: do hydrodynamic equations even make sense? Okay, so let me talk about relativistic things. So let's say you're a student in subatomic physics or astrophysics, and you want to learn about relativistic Navier-Stokes equations. Say you want to study the quark-gluon plasma or neutron star mergers. And as a student, you might want to learn about fluid mechanics from classic textbooks. And if you come from Soviet education system like I did, there is a certain Bible that's called Landau and Lifshitz, and there is volume 6 of that Bible. It's called Fluid Mechanics, and you open it and you see some hydrodynamic equations. Then I came to the West, and in the West there are other Bibles. So I had a copy by Weinberg, Gravitational Cosmology by Weinberg. And also in that book, there was a chapter about relativistic fluid dynamics, and there were some hydrodynamic equations. And you look at them as a student, and you see that these equations look very different. Okay, so these are equations due to Eckert in Weinberg's book, and this is Landau-Lifshitz formulation. And these equations look different. And you're puzzled as a student. But then, okay, so what? As a student, you're taught to shut up and calculate. So let's shut up and calculate, and let's work out the simplest possible example, that is infinitesimal linearized perturbations of the thermal equilibrium state. And both Landau and Lifshitz and Eckert's theories, they predict 2 things. Number 1, thermal equilibrium does not exist. And number 2, things propagate faster than light. So the equations are different, but they have these 2 things in common. Now, this is embarrassing. It's sad, but it's true. The equations that you find in the classic textbooks, they make no physical sense. This has led to the belief that the Navier-Stokes equations cannot be unified with Einstein's relativity and have to be abandoned in a relativistic setting. So what happened instead is that other exotic theories have been proposed in the 1970s to replace the Navier-Stokes, and the field has moved on. So it is these other exotic theories that people use in practice if they want to simulate, say, the quark-gluon plasma, not the Navier-Stokes. But as a student, you still have this nagging question. Why do the theories of Landau, Lifshitz, and Eckert, why do they differ in the first place? And to understand why, let's talk about temperature. Okay, so I'll let you read this XKCD cartoon. Okay. So I don't know if you find it funny, but the point is temperature has units. It depends on how you measure it. So temperature is only something that is unambiguously defined in equilibrium. And by definition, as we teach our students, T is the quantity that is measured by thermometer. And what I have here on the left is a cartoon of 2 identical equilibrium states in their boxes. And I have 2 different thermometers, the red thermometer and the green thermometer. So this is the heat reservoirs of the thermometers. They're connected to their gauges. And in identical equilibrium states, these two different but correctly calibrated thermometers, they will show the same temperature. Right? That's to say, temperature is well defined in equilibrium. But in identical non-equilibrium states, exactly the same two thermometers will show different temperatures. So what I have here, I have two identical non-equilibrium states, and I stick these two thermometers in identical non-equilibrium states, and they will show different temperatures. And you know this very well. You can have two thermometers, two different models of thermometers outside your window. And when the wind blows or when the temperature changes, you know, the two may show different temperatures, even though in equilibrium inside your room, they will show the same temperature. And this is because it may take, you know, different time to adjust for these thermometers, different times to equilibrate. The shapes may be slightly different, and so on. So this means that whenever we talk about temperature, we have to talk about conventions. So there is arbitrariness in what you mean by fluid temperature, and that is because your choice of a thermometer is a convention. And there is also some arbitrariness in what you mean by fluid velocity, and that is because your choice of velocimeter is a convention. And Landau-Lifshitz equation version of Navier-Stokes, they use one convention, and Eckart's version of Navier-Stokes uses another convention. And because of that, there is simply no such thing as, so to say, the Navier-Stokes equations. There is no unique Navier-Stokes equations. There are infinitely many Navier-Stokes equations, and they differ by your arbitrarily chosen convention. Now, what's important is this. Different Navier-Stokes equations, different conventions, they give rise to different mathematically inequivalent Navier-Stokes equations. So this is not a typo. What I do mean mathematically inequivalent. So the conventions have real consequences. And this is because the Navier-Stokes equations, they only give a crude approximation of a real fluid. The difference between these conventions is hidden in the crudeness of these approximations. Or maybe to be more precise, that's hidden in the high derivative terms in your derivative expansion. So Landau, Lifshitz, and Eckart adopt different conventions for Navier-Stokes, but both are bad and both lead to nonsensical predictions. So what exactly is wrong with the classics? So it's actually quite easy to understand. Both Landau, Lifshitz, and Eckart, they define temperature using the following relation. So they say that the exact non-equilibrium energy density is given by epsilon of t, where this is a function that is given by the equation of state. Now, the non-equilibrium energy density is, of course, the equilibrium is the non-equilibrium expectation value of you know, certain component of the energy momentum tensor, and you know, it has a well-defined microscopic meaning. Doesn't care about any conventions at all. So this distance is something that's exactly well-defined microscopically. And this is something that we say it's E of t given by the equation of state. And so what this means as the local energy density changes, the thermometer adjusts its temperature instantaneously, right? So the moment this changes, T changes as well, instantaneously, like that, just because this is how non-equilibrium temperature has been defined. And you can translate this, to saying that such thermometers violate relativity and they lead to superluminal propagation in relativistic fluid dynamics. So you can say, wait, okay, so if the convention by Landau, Lifshitz, and Eckart, they don't work, why don't you choose a different convention? Why don't you choose a thermometer or velocimeter that does not react instantaneously and respect relativity? So can you just adopt a sensible convention? And the answer is yes, you can. With good conventions, the equilibrium is stable, signals propagate slower than light, the equations are mathematically well posed, and can be coupled to Einstein's gravity. So how does this work in practice? So let me show a few slides in terms of how this works in practice. So, so the way to think about hydrodynamics is the best way to think about it as some kind of effective theory. It's not effective field theory at this point, but think about it as effective classical theory for things that are locally near thermal equilibrium. So what we always do in effective field theory, we do these 4 steps. So first we identify the low energy variables. Then we write down all the terms that are allowed by the symmetry. Then we do this up to a given order in up to a given dimension. So here I just took 5 to the 4th theory in 4 dimensions, and I wrote down all things up to dimension 4. And number 4, we constrain the coefficients in the effective action to be such that the physics is sensible. For example, the sign of this coefficient has to have a definite sign in order for the vacuum state to be stable. So let's do the same in hydrodynamics. So this is actually sort of a little bit revolutionary. if you think about it, it looks trivial, but this is not what people have historically done in hydrodynamics. So let's do the same in hydrodynamics. You identify the low energy variables and you take them to be the variables inherited from equilibrium, inherited from thermodynamics, temperature, velocity, chemical potential. You write down all possible terms in the constitutive relations that are consistent with the symmetry. You do this up to a given order, say first order in the derivative expansion to get Navier-Stokes. And then you constrain the coefficients so that the physics is sensible. For example, you demand the stability of equilibrium. And when you do this, you do get equations that are that do make sense. So here is a very simple example of these ideas. So let's look at conservation of single current that maybe describe the diffusion of some conserved density, baryon number, or some other U1 charge that you like. To have a classical closed set of equations, you express the charge density and the spatial flux in terms of some useful quantity, which I call mu, which you can think of the chemical potential of your conserved charge. And the spatial flux is, to leading order in derivatives, is some constant times the derivative of gradient of mu. And if you think about the charge density, you can write down the first term proportional to mu with some proportionality constant, which I just called chi, plus something that is the time derivative of mu. So that is actually allowed by the symmetry, so this term. And if you ignore this term with the time derivative of mu, you get the diffusion equation as before. And if you keep the term with mu dot, you get in the conservation equation, you see when you take the time derivative of this, you get the second time derivative of mu, and you get the second space derivative of mu, and the equation is hyperbolic, right? So the diffusion equation is parabolic, this one is hyperbolic. The structure of the equation has changed. Now this equation you can talk about in the context of relativity, and this one you cannot. So why don't people usually neglect this term? So why nobody writes it down? The reason you don't write this down is because this term can be eliminated by field redefinition and truncating your derivative expansion. You always work to a given order in derivatives. You always truncate the derivative expansion in any effective field theory. And this one can be pushed to higher orders in derivatives by field redefinition. And then you truncate and you forget about it. So this term is not physical for the purpose of correlation functions, or for the purpose of classifying the transport coefficients, but it changes the structure of the partial differential equation. And physically, the coefficient of this term can be interpreted as specifying your mu meter, not thermometer, but mu meter. So the bottom line is this. Unifying Navier-Stokes with relativity was thought to be impossible for many decades. But you just need to choose a physically sensible thermometer velocimeter, and then the Navier-Stokes equations are happily unified with relativity. They were written down not that long ago. They're still waiting to be solved. They're still waiting for the numerical codes to be developed. And the lesson for students here is this. So if you're reading the classics and they don't make sense, well, just rederive everything using your own way. You may as well discover something that's new. So that was my first story. So my second story is this. Are there limits to improving the hydrodynamic equations? So here's a first look at the limitations of hydrodynamics. So we know that macroscopics is made out of microscopics. So here is a cartoon of what microscopics looks like, some microscopic constituents, some distance, typical microscopic distance scale. Then we have an effective macroscopic theory, right? So we solve our equations, we find some profiles in space of temperature, velocity, density, whatnot, And there is some scale, capital L, which is the distance scale of your solutions. Right, and you may think that this effective classical description is probably okay when this capital L is much bigger than the small l. In other words, when the derivatives of this function in blue are small. On the other hand, if the scale of your solutions, capital L, is comparable to small l, you probably should not trust these solutions that come out of your classical equation. So hydrodynamic is probably not okay when capital L is about the same as small l, in other words, when your function has large derivatives. So this suggests the idea to organize hydrodynamics as an expansion in derivatives, just like you do in any effective field theory. You organize this as an expansion. You assume locality on large distance scales and time scales, and you organize your theory as an expansion in derivatives. So here's what I have. I have something that I denoted by superscript 0 with no derivatives. Then I have something with superscript 1 that has one derivative, 2 derivatives, and so on. Okay, so the question you can ask, can you keep improving forever? So let's say you generate an infinite series in the gradients, all the way up to infinity. Does the series converge or diverge? Okay, so if the series converges, then this tells you that your effective theory can be systematically improved to include more and more transport phenomena. So hydrodynamics can be improved. And if the series diverges, then hydrodynamics is not supposed to work. Then why does it work? Is it really a fluke? So what exactly is the expansion? So argued we need to look at the expansion in gradients. So let's look at the simplest possible solutions of hydrodynamics that are plane waves. In this case, the derivatives are just I times k. So the hydrodynamic expansion is expansion in powers of k. So for example, if you look at sound waves, so this is what we teach all our students in beginning physics classes, the dispersion relation, the relationship between the frequency of sound and the wave vector k here. So it looks like this. So it has something that is proportional to the first power of k. The coefficient is the speed of sound. There is a plus minus here because you have two waves propagating to the right and to the left. And there is something that's proportional to k squared. And the coefficient here is proportional to the viscosity. So it has an I here. It tells you about the dissipation of sound waves. So then there is this dot, dot, dot. So this dot, dot, dot will come from higher orders in the derivative expansion. And you can ask, so do this series, when you have omega as a function of k, so do this series converge or diverge in hydrodynamics? And the question is quite complicated. So for example, if you want to answer this question in weakly coupled quantum field theorem, say simplest case 5 to the 4, then computing, say, this coefficient b amounts to computing the viscosity, shear and bulk viscosities in weakly coupled 5 to the 4 theory, which is a very, very non-trivial exercise. It involves very, very tricky resummations, identifying the right classes of diagrams. You need to carefully look at small angle scattering and gauge series. I mean, it is a mess, a complicated, very complicated thing. Now, if you look at k cubed, k to the 4, I mean, these are not easy exercises to compute, even an infinitesimally, weakly coupled field theory. And then you want to sum this thing all the way to infinity. So in weakly coupled QFTs, it's quite difficult to answer. And I don't know how to answer this in general. So let's look at simplest examples. So I'm going to look at analytic examples. So there are fluids that can be studied analytically using holography. So these fluids, morally speaking, are similar to the coagulant plasma produced in nuclear collisions. So that's how I think about them. And in the simplest holographic examples, which is n equal 4 super-n mils and its relatives and 3 plus 1 dimensions, what we found is that the sound wave omega is a function of k is indeed an analytic function of k. It is convergent within some domain for sufficiently small wave vector, and the convergence radius is determined by temperature. There is root of 2, there's a 2 pi, whatnot. So the convergence, to me, it gives me hope that hydrodynamics is improvable. So what I want to comment now is, why is there a critical value? Why is there a critical momentum or critical wave vector in the dispersion relations in these field theories? And the example that I want to emphasize is an example from elementary math. So look at a function f of x is equal to 1 divided by 1 plus x squared. So here is a plot of this function. So this function is a perfectly smooth function of x for all x from minus infinity to infinity. But if you look at the Taylor expansion of this function around the origin, so that Taylor expansion only converges when x is less, the absolute value of x is less than 1. So why is this so? There is no singularity when x is 1. It's a perfectly smooth function. So to understand why, we need to, of course, take x complex. And then the reason is that in the plane of complex x, there are singularities at plus minus I. And I is located at a distance 1 from the origin. And so that's why it only converges when absolute value of x is less than 1. So similarly, what happens in hydrodynamics is that omega of k, they're smooth functions at real k. And to understand why these functions only converge for up to some critical value of k, you must take the wave vector, the momentum complex. So complex omega and k. So what we teach our students is that in classical physics, dispersion relations omega of k, they come about by solving equations like this. You have some function omega and k squared is equal to 0, so it's k squared if your system is rotationally invariant, where f is determined by the equations you want to solve, say hydrodynamic equations or Maxwell's equations in matter or whatnot. So let's say you take this diffusion equation, and for plane waves, it's clear that one time derivative gives you minus r omega, two space derivatives give you minus dk squared. So this whole thing is gives you this capital F, which looks like that. So for sound in viscous fluids, it looks a little bit more complicated. So it has omega squared. So this is speed of sound squared k squared. So this is what we teach our students in first year physics. Then there is some dissipation due to viscosity. So when we, again, teach our students about waves, we talk about two things. So the first thing we talk about is we say, oh, let's take omega to be real. Then you solve this equation. And it turns out that in general, you can only solve this equation when k, the wave vector, is complex. And then you interpret the imaginary part of k as the damping length or the penetration depths of the wave as it propagates inside the material. And another thing we tell our students is we say, oh, let's take k real. And then it turns out you can only solve this equation for omega complex. And then you interpret the imaginary part of omega as the relaxation time for the wave in matter. Now, what happens if both omega and k are complex? So this is not something we teach our students. This is not normally something we talk about in physics. So I want to talk a little bit about these oscillation modes at real k. So what you're looking at is a picture of singularities of the energy density response function in the plane of complex frequency. So they come about as quasi-normal modes of black brains in if you use holography. So, but these are basically solutions of this function capital F is equal to 0, right? So real part frequency or imaginary part of frequency in some units, and this is all at a certain value of spatial momentum, which in these units is 1 in units of temperature. So what are these dots? So each dot is an oscillation mode of a fluid. These two dots are sound waves. So the dispersion relations look like this. Like I said earlier, they have an expansion in powers of k starting with the first power. So think about these oscillation modes as something that is macroscopic. You can describe them using classical equations. You know, since maybe 18th century or 19th century, you knew how to write down these equations. And these modes approach the origin as you take the wave vector to 0. Now, these other ones, they're microscopic oscillation modes. They have no classical interpretation. You don't know what they are. They're not described by Navier-Stokes or anything. There's some microscopic stuff that, you know, decays very, very quickly on the microscopic time scale. They stay away from the origin as you take the long wavelength limit of small momentum. Okay, so this was for real k. Now I want to look at complex k. Okay, so the way I'm going to look at complex k, I'm going to take my momentum, or in this case, momentum squared, and I'm going to give it a phase. So the picture you're looking at right now is the picture when q squared, which is my momentum in units of temperature, is equal to 1. Now I'm going to give it a phase, 1 times exponential I theta, and I'm going to change this phase from 0 to 2 pi. So as the phase changes, the phase of my complex momentum changes from 0 to 2 pi, these dots are going to move in the complex plane somehow. So the way they move are like this. So the phase is equal to 0 here, and now the phase changes, and the phase is equal to 2 pi is here. So what you see has happened is that this blue and the gold ones, they have swapped places. But they still remain sound modes. Now, if you take your momentum to 0, they will still approach the origin. Okay, so now I'm going to show a very similar picture for complex, again, K, but now my K squared in units of temperature is 1.99. Okay, now this is the picture when the phase is equal to 0, and now I'm going to change the phase from 0 to 2 pi. So that's how they move, and the phase now is equal to 2 pi. Okay. So these two modes, blue and gold, they still swap places, and they swap places because I'm changing q squared, and these are sound waves whose dispersion relation is proportional to momentum, frequency proportional to momentum, not momentum squared. So that's why there's a branch cut there. So, so they swap places, but they remain sound modes when theta becomes equal to 2 pi. And the next picture I'm going to show is the picture when my K is complex, but instead of 199 is 2.01 in units of temperature. And this is, again, this is a picture that you obtain for quasi-normal modes of non-extremal black brains when you use holography. Now, this is when the phase is equal to 0, and now you change the phase from 0 to 2 pi, and they move, and so this is the phase equal to 2 pi. So what you see has happened, the sound modes with the blue and the gold. Now this gold, so this one used to be the sound wave, but it's now here. Now if you take momentum to 0, this one will approach the origin, and the green one will approach the origin, but this one will stay away from the origin, right? So these two are now sound waves, and this, it used to be the sound wave, but it's not a sound wave anymore. So a classical excitation has become a non-classical excitation. So these two pictures is the same information you have just saw in the videos. They show you the paths that are traced out by those trajectories. And what you see as you go between 1.99 and 2.01, the topology of these trajectories in the plane of complex frequency changes. And the way you can have this topology change is, of course, something singular has to happen. So the singularity in question here is marked by this red asterisk, and it is the collision of poles, right? It's the collision of singularities. So when your momentum squared is equal to 2 in units of temperature, the modes collide, the topology of the trajectories changes. So what you're looking at level crossing in macroscopic dissipative systems. So this level crossing tells you that a classical hydrodynamic excitation becomes a non-classical excitation. And this collision between classical and non-classical excitations is what determines the convergence of the hydrodynamic expansion. So this is what gives you the critical wavelength for sound waves. And in order to see the emergence of this critical wavelengths, it is crucial that you look at complex momentum and complex frequency. So the bottom line is this. In many solvable examples, your classical macroscopic excitations and non-classical microscopic excitations, they're merely different branches of the same multi-valued complex function, which I find quite illuminating. So my final story is this: why everything I said so far is wrong. So here is my second look at the limitations of hydrodynamics. Okay, so macroscopic stuff is made out of microscopic stuff. So if you think about the relationship between classical mechanics and quantum mechanics, in a quantum vacuum, virtual particles are constantly produced and absorbed due to quantum fluctuations. Similarly, in a macroscopic state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. The sound waves will backreact on the macroscopic physics, and they will backreact because hydrodynamics is not linear and waves interact. So here I have a cartoon where I have a fluctuation in a fluid here, and this fluctuation has produced sound waves that propagate in all directions. And this fluctuation-induced sound waves will interact with this thick line, which I thought was my original sound wave. So should you care about the back reaction of those fluctuations? It depends on the questions that you ask. So the relationship of hydrodynamics to microscopic physics is like the relationship of classical mechanics to quantum mechanics. So if you look at correlations, then you know that classical versus quantum predictions can differ dramatically. So similarly, if you're interested in macroscopic, long-time, long-distance correlations, macroscopic correlations, then classical hydrodynamics, which ignores the back reaction, that can lead to dramatically wrong prediction. So let's look at a simple example. So simple example is viscosity. So what is viscosity? Viscosity is a measure of the transfer of momentum between layers of fluid. So here is a picture. I have a flow of fluid going from right to left here. So this thick yellow arrows is the flow of my fluid. It has the gradient of the x velocity in the y direction. So Txy, the special stress tensor, is proportional to this y derivative of the x velocity, and the coefficient is precisely what you call viscosity. So how is this momentum transferred between layers of fluid? It transfers because particles can jump from one layer of fluid to another layer of fluid. And when they do, so this particle takes its large momentum on the bottom and transfers it to a layer with small momentum on the top. So that's how this configuration relaxes. So this is the physics of viscosity. You can relate this to correlation functions of the stress. And it looks like this. So it will have a zero derivative contribution from pressure and one derivative contribution from, it has one power of frequency. So the coefficient is viscosity. So in a gas, it has been known for a long time that the viscosity is proportional to the mean free path, basically the average distance traveled by these particles. Now, why am I talking about this? So I'm talking about this because momentum can also be transferred by collective excitations. So collective excitations, like sound waves. So here is exactly the same picture where I have sound waves that are induced by fluctuations. And they can travel around my fluid and they can transfer momentum. Now, the sound waves, they don't propagate infinitely far away, they damp. They damp because of viscosity. So the mean free path, how far they propagate, is determined by the viscosity, like this, and by the wavelengths of the sound wave, like this. So when you think about the contribution of these waves to viscosity, so what you do is you sum over all possible waves with all possible wavelengths. So basically I have to integrate over all capital D number of space dimensions. And this is your mean free path. So T here is for units, but basically the point is here you have 1 over viscosity and here you have 1 over k squared, because longer wavelengths, they propagate further. And you integrate up to some cutoff, which is the UV cutoff of the effective hydrodynamic theory, like the interparticle spacing or whatnot. And so what happens, you see, is like this. In 3 special dimensions, you have a contribution to viscosity, which is inversely proportional to the viscosity itself. But in 2 special dimensions, you get an integral that is infrared divergent. Okay, and this tells you that this physics of fluctuation does something interesting in 2 dimensions, but also in 3 dimensions. So the way people usually try to quantify those pictures is to come up with some kind of systematic description of this. And the first description that people came up with was so-called stochastic hydrodynamics. So it's an attempt to convert hydrodynamics to field theory, statistical field theory. And the way you do it is you say, okay, so here is, for example, my stress tensor, and it you express this in terms of the fluid velocity. It has some form. So the important one here is this one, which is effectively fixed by boost invariance. But you add to it something that is not present in classical hydrodynamics. You add some kind of stochastic noise. So it's exactly like doing Brownian motion with the Langevin equation. Right? So it's essentially the Langevin equation, which is whose idea is translated to hydrodynamics. Now, this noise has some correlations, which are normally taken to be Gaussian correlations. So if you look at the correlations of the stress, they can be translated to the correlations of the noise here. And if you do it, what you will find that the stress correlations will have a contribution of what you naively would think as the viscosity. So in the language of QFT, you would call this the bare viscosity. And then you would have the one loop correction that will come from this interaction vertex. You see there are two velocities here and energy density plus pressure. So you have energy density plus pressure sitting at each vertex, and you have velocity-velocity correlation that sits here. And so this one loop diagram will renormalize what you naively would think as the bare viscosity. It corresponds to this picture. So if you look at exactly what happens to the correlations of stress. So here is this formula. So it's a bit messy. So let me look at each term here. So the terms that are marked by red. So these are the terms that come from classical hydrodynamics. And so these are the terms that that come about if you ignore stochastic fluctuations. So this formula is written in 3 special dimensions. In 2 special dimensions, there would be infrared logarithmic divergences. But this is in 3. So this P is the pressure, it has no derivatives. This omega is the frequency that comes from one derivative hydrodynamics. The coefficient here is the viscosity. And there are some higher order things. So the terms in purple are the terms from these one loop corrections. Right? So some cutoff dependent contribution to pressure. Okay, so that's boring. There's now some cutoff dependent contribution to viscosity. Okay, it's cutoff dependent, but it's more interesting actually because it is inversely proportional to the viscosity, as expected on the grounds of that simple cartoonish picture that I showed earlier. And then there is this. So this is cutoff independent. It's universal, and it gives rise to late time correlations. Okay, so this is the one loop correction to viscosity, actual physical viscosity. If you were to actually measure it, it would include all such corrections. However, what you see is that small viscosity, so S is the entropy density, so small viscosity over entropy ratio implies large corrections to viscosity over entropy ratio. And this tells you that fluctuations are mandatory for small viscosity physics. So if you do physics of small viscosity, you cannot just do partial differential equations of classical hydrodynamics. You have to include these fluctuations. And what it also tells you is that in 3 special dimensions, these fluctuations are more important than second order hydrodynamics. So these are infrared contributions right here that are determined by thermodynamics, the equation of state, and the viscosity over entropy density. So these are fluctuation effects that are more important than second order classical hydrodynamics. And if you go to 2 special dimensions, they actually will be even more important than first order hydrodynamics. So here is an analogy with quantum gravity, right? So I talked about this using the language of viscosity and hydrodynamics, but exactly the same thing happens in perturbative quantum gravity. So in classical hydrodynamics, what you do is you write down your constitutive relations, 0th order perfect fluids, and they give you some order 1 contribution to the response function of stress, as I showed on the previous slide. Then there's one derivative hydrodynamics and gives you order omega, 1 derivative contribution to stress correlations on the previous slide. And then there's some 2 derivative classical hydrodynamics that gives you omega squared, but there's this omega to the power 3/2 that comes from the fluctuation correction. And this is more important than omega squared. And so it's an example when fluctuation effect is more important than classical effect. And in perturbative quantum gravity, the same thing happens. So if you look at the perturbative, if you look at the derivative expansion of classical gravity. So here is the Einstein-Hilbert theorem, and then you have some high derivative corrections that sit here, and they come from these corrections come with some coefficients. So these coefficients, they will carry dimensions, so they will be suppressed by some higher, some higher energy scale, Planck scale, string scale, whatever, some higher energy scale. And now, if you look at the contributions of these terms to the two-particle interaction potential, okay, so it looks like this. There is going to be a Newtonian piece from here. There is going to be GR correction to the Newtonian potential, like this. Then these high derivative terms, they will give you exponentially suppressed contributions. But if you look at the one loop graviton exchange, if you actually include the graviton loop and do the loop integral, you will get a correction that is a power law. Right? So it's described in great detail in the series of papers by Bjorn Bohr, Donahue, and Holstein 20 years ago. So what you see here is that this quantum correction that comes from the graviton loop, it's actually more important than the classical correction that comes from this classical high derivative gravity. And the physics of these two things is pretty much the same. You have a theory with massless degrees of freedom. You stick massless degrees of freedom in the loop, and they will lead to infrared effects. So the bottom line is this. Using classical hydrodynamics, meaning if you think about hydrodynamics as partial differential equations, if you use classical hydrodynamics to evaluate correlations at arbitrarily long times, arbitrarily long distances, that is unreliable. So your short time statistical fluctuations, they give rise to infrared late time correlations. And the deviation from classical hydrodynamics are more pronounced at small viscosity. So stochastic hydrodynamics, it predicts that these infrared correlations are universal. They're determined by thermodynamics and transport coefficients. And there are some universal answers that go beyond what you thought was classical hydrodynamics. But actually things are even worse. So things are even worse for classical hydro, that is for thinking about hydrodynamics as partial differential equations. And this is because this simple stochastic hydro that I outlined in the previous slides, so people have been doing this for many years, but it's not systematic. It does not include the derivative expansion, does not include the non-Gaussian noise, does not include the nonlinear fluctuation dissipation theorems. To me, the most interesting development in hydrodynamics in recent years was the emergence of these effective field theories that do all of those things, and they include stochastic hydrodynamics as a special case. So these effective field theories, they're formulated sort of like, morally speaking, similar to a double sigma model, and they have to be formulated on the Schwinger-Keldysh double time contour. So I put a link to a review paper by Honglu and Pavel Glorioso that talks about these effective theories. So the only thing that you need to know about these effective theories, if you haven't looked at them before, is there are two types of fields. One type of field is what you would call the classical field, or phi r, and the other type of field is what you would call the stochastic field phi a. So morally speaking, think about this as, if you think about the Langevin equation for the Brownian motion, or about the stochastic hydrodynamics. So this is the classical part, and this is like the noise part. So phi a comes from the noise, and this is the classical contribution. Okay. So these effective actions, they're organized as a derivative, as an expansion in powers of phi a, in powers of the noise. The first term that you write down, so the effective action has to have such structure that it vanishes when phi a is equal to 0. So the first term is a linear term in phi a. So terms like this, phi a times some function of phi r. This function can be complicated nonlinear function. So these are nonlinearities of classical hydrodynamics. These are interactions in the effective action. This S is the effective action. So these terms are fixed by the classical constitutive relations. Okay. Then there are other terms that look like phi squared, phi a squared, some function of phi r. Now, some of these terms are fixed by the fluctuation dissipation theorem in terms of the classical transport coefficients and viscosities. And in these two terms is what gives you the stochastic hydrodynamics that people have been talking about since 1950s. So this is the hydrodynamic analog of the Langevin equation for Brownian motion. Now, but there is more. So some of these terms that are quadratic in phi A and some nonlinear functions of phi R, some of these terms actually not fixed by this fluctuation dissipation theorem, and they're invisible to classical hydrodynamics. So the coefficients of these terms is not something you would ever know if you only knew about classical hydrodynamics. And of course, there are terms with more than 2 powers of phi A times some function of phi R. And these terms are, of course, also invisible to classical hydrodynamics. So the way I think about these terms here, these are basically new interactions in effective theories that people have ignored up until very, very recently. And these are some terms in the effective Schwinger-Keldysh field theory. And the coupling constants that sit here, the coefficients of these types of terms, you can call them stochastic transport coefficients. And the coupling constants that sit in front of these terms is what you would call normal transport coefficients. So this would be viscosity, heat conductivity, whatnot. They sit in the Schwinger-Keldysh effective theory in these 2 terms. Now, why am I talking about this? I'm talking about this because the stochastic transport coefficients, they lead to a breakdown of classical universality. So these stochastic coefficients, they contribute to measurable correlation functions through loops, not at tree level, but through loops, they do contribute. And of course, loops give rise to infrared effects. So the stochastic transport coefficients, they give rise to infrared effects. Though they happen to be derivative suppressed in 3+1 dimensions, they will be less suppressed in 2+1 dimensions. Again, depends on the interactions, whether the interactions are derivative interactions, non-derivative interactions, kind of depends what that determines relative importance of those terms. So the stochastic transport coefficients, or the coupling constants of those terms, they can only be matched to the microscopics, to the UV of the theory through non-retarded functions. So this is very different from the viscosity and heat conductivity or charge conductivity. From here, they can be matched, these coefficients can be matched to the UV of the theory through so-called Kubo formulas by using retarded response functions. These ones cannot. You need other types of functions that are not retarded, not advanced, some mixture of retarded and advanced functions that determine these coefficients. And so what this tells you is that knowing the macroscopic classical effective theory to all orders in the derivative expansion is not enough to correctly describe macroscopic infrared correlations. Okay, so that's something that I wanted to emphasize. If you only know classical theory and you want to describe macroscopics, not enough. You need some genuinely new information. So where does this leave us? Okay, hydrodynamics, does it even make sense? So for many years, I had this dream of a grand unified theory of hydrodynamics that applies to many different kinds of fluids. It ensures that the equations are sensible in the sense that I talked about at the beginning of the talk. They would be hyperbolic for relativistic systems, for example. It allows for systematic improvements through the inclusion of fluctuations, quantum effects, derivative expansions. Predicts macroscopic correlations. Oh, I didn't talk about quantum chaos. But there was an intriguing line of development from holography a few years ago that claimed that hydrodynamics at complex momentum is actually related to quantum chaos. So information about that would be connected in the grand unified theory, and of course it would be nice if it was experimentally verified. And these lines of research are about effective theories. It actually, for me, I'm quite optimistic that this vision of grand unified theory is coming to being true. So I want to end with an encouragement for students. So as a student, one often tends to think that all interesting questions in physics have already been answered many years ago by the great. And hydrodynamics is an ancient field by modern standards, and people are still trying to figure out some very basic questions. So if as a student you work in a field that is less than 200 years old, do not lose hope. there's surely many fundamental things that are left for you to discover. And as I have seen, as you have seen in this talk, some of these things come from holography, and some of these things come from very funny types of field theories. So I'll stop here. Thanks for listening.
Thanks. You can all unmute if you want to. So are there questions? Yes, Tam?
Yes, hello.
Hey.
I hope that yeah, there it is. I'd like to ask the following question with regards to your remark that these fluctuations are not described by correlation functions that are either retarded or advanced, but they are mixed. And of course, that immediately brings to mind whether, you know, the Autok type of functions might be useful probes in this regard. Right,
good. So Autoks is another level of complication on top of that, and the reason is the following. So there are only two types of fields here, phi r and phi a, and the reason there are only two types of fields is because these are effective theories that are formulated on the Schwinger-Keldysh contour. So phi r is roughly the difference, or the average of the fields on the two branches of the Schwinger-Keldysh contour, and phi a is the difference of the fields on the two branches of the Schwinger-Keldysh contour. Now, in order to describe Autoks, you need a contour which is more general than the Schwinger-Keldysh contour. You need the one that goes back and forth twice. So this would mean that in order to describe that, something like this, I would think, is not enough. You would need to have another type of effective field theory that is now formulated with more than these two fields. Right.
Is there any hint of what these other degrees of freedom could be?
Oh, well, right. So mathematically, you would know what these other degrees of freedom are. This would be like the average or the difference between the fields on different branches of the Schwinger-Keldysh contour. Physically, what they correspond to physically, I don't know. I really don't know. Here we can give them some interpretation as, you know, the noise field and the classical one, or you don't even have to do finite temperature physics. You can do zero temperature physics with this kind of Schwinger-Keldysh. This would be like quantum effects versus the classical background. But if you have more than once going back and forth, I don't have a physical intuition for what these things do. I think this would be. I mean, I would be interested if the field went in that way. Yeah.
Can I ask a question?
Sure, go ahead.
So you shown that when you do loops in the effective fields of hydrodynamics, you do get important corrections in the infrared. Now, in theories where, for example, holographic theories, such corrections are multiplied by a small parameter, which is 1/n squared. And therefore, although in the ultimate infrared, of course, they might dominate the subleading corrections, this will transit at some point. And therefore, for several practical cases, they may not be very important. So can you comment on this, and in particular, when they are expected to be important in more practical cases?
Right. So we actually commented on this in this paper with Gaimon and Paul Romashke in 2011, here, 1104. And the way you need to plug in the numbers because these corrections, they have viscosity and they have thermodynamic functions. And, you know, as you pointed out, in large N theories, there would be, you know, large N suppressed. Now, if you think about QCD at, you know, the temperatures that, you know, people talk about, you know, at TRIC, at LHC, well, QCD is N = 3, not infinity. Temperature, you know what it is. The equation of state, you know what it is from lattice simulations. And then you can ask, how important are these effects and these effects if you take, say, to be eta over s to be 1 over 4 pi. Okay, and actually, it turns out that they're not negligible. So I don't remember the exact numbers, but if it is, you know, if it is 1 over 4 pi, you can look up the exact numbers in the paper. I don't remember, but if it is 1 over 4 pi, it's maybe like a 20% effect, if I remember right. But if it is less than that, it can be a 50% effect.
Okay, I see. Thank you.
So yeah, so actually, if you really want to push, so the thing is, if you really want to push, if you really want to study QCD with eta over s of order 1 over 4 pi, then these things are not tiny. They may not be huge, but they're not tiny.
Okay, thank you.
Can I ask a follow-up question?
Sure.
So people in combat are looking at electron hydrodynamics these days.
Yep.
Do you have any idea of what the numbers would look like? They already face all sorts of subtleties to distinguish between truly hydrodynamic effects and effects that you can still get from kinetic theory, from Boltzmann, from solving the Boltzmann equation, essentially.
Right, right.
So if on top of that they have to worry about long time tails, then
right. So I don't know, and one reason why, you know, I don't know is that what exactly these effects are. They depend on what exactly hydrodynamics is, right? So if you do, say, Lorentz invariant hydrodynamics, right? So it's one kind of thing. If you do Galilean hydrodynamics, it's another kind of thing. The numbers, you know, would be somewhat different, I think, if I remember right. So there was actually a discussion of these effects in Galilean hydrodynamics by Thomas Schäfer and somebody else whose name I forgot. Sorry, around the same time, 2012, I think. Now in these Condmat systems, I wouldn't necessarily know if the hydro is like genuine Lorentz invariant hydro, or if it is genuine, you know, Galilean hydro, or if it is like something else that's mixed. So
so they usually take it to be Galilean hydro with some momentum relaxation term, but certainly not relativistic.
Right. So the physics of this effect is certainly not specific to relativity. I mean, Galilean hydro has exactly the same type of effects, but I actually have not plugged in the numbers. I think what was done in that paper by Thomas Schäfer, and I think even maybe Paul Ramashke and somebody else, they also had a paper about about these effects in Galilean hydro, but their emphasis was on cold atomic gases. Right, so they had some numbers for cold atomic gases, but I don't recall them having any numbers for electron fluids. Though I think it should be quite straightforward to plug in the numbers and see what the effects are. I have not done that. See the magnitude of the effects. I have not done that.
Okay, thanks.
I ask a question on that too.
Yeah, go ahead.
Precisely about this term, this omega to the 3/2. If I understood correctly, it's a term that comes from a one loop calculation.
Yep.
One loop contribution. So in a theory like QCD, which in principle and even in practice, it is possible to calculate a lot of things. I'm just wondering how sensitive is this contribution, which is of course cutoff independent, to higher loop corrections, first of all, or eventually whether it's known what can we see on the lattice for non-perturbative effects. But already for higher loop corrections, what could happen to this term if one were to take higher loop corrections?
You would get higher powers of omega.
Oh, so this term is not going to be affected by higher loop,
No.
even though it's come from a one loop calculation.
Yes. Yes.
I guess you can get the powers just by power counting, right?
You can get the powers by just power counting. Yes. Yes, you can do scaling analysis in that effective theory. And you know, there is a sense in which you know, certain, you know, vertices will be more irrelevant than others in the infrared of this effective theory. So this analysis can be done.
But it doesn't break. But this analysis of the effective theory doesn't break down when this term becomes interesting or something happens.
Well.
That's why I'm asking for QCD, because they're possible to push the calculation further.
Right. So the question is whether the theory is weakly coupled, whether the effective theory is weakly coupled or strongly coupled, right? And it's different from the question of whether the underlying quantum field theory is weakly coupled or strongly coupled. Here, it's sort of, you can see the theory will be more weakly coupled if eta over S is large, right? So if eta over S is small, then in principle, you know, even in here, then these higher loop corrections, you know, will also be important. And if this effective theory is strongly coupled, then I just don't know what to do with it. It's a non-renormalizable effective field theory formulated in the derivative expansion, and if it is pushed in the strongly coupled regime, so it's not like lattice QCD. Lattice QCD, by the way, cannot see any of this, right? Because lattice QCD is Euclidean. This is real time.
Okay, so you need to be in real time to see any of this.
You need to be in real time. That's right. That's right. So this is all real time physics. Yes. So where this thing can be, for example, useful for lattice QCD is if one wants to match the Euclidean lattice results to some kind of real-time profile, right? Then you need to know what the real-time spectral function looks like, and these things, they definitely do contribute to the real-time spectral function.
Other questions? Well, if not, we can thank Pavel again.
Yeah, thank you.
Thank you.
Thank you so much.
And I will turn off